from last class, I'm just going to do a very brief recapitulation of the concepts, because some of you might be aware of these concepts and some of you might be new. So I'll anyway go through them one more time. So just to rehash, right, what we did last time was the processing unit consisting of the arithmetical and logical unit, which is a combination of different circuits. Both arithmetic operation and logical operations are performed in these circuits. As I said, there could be addition operation, multiplication operation, or even logical operations like AND, OR, and so on. And these operations are executed on a set of data, right? And this data could be coming from the registers, right, that are internal to the CPU or the processing unit, or it could be also loaded from an external memory, right, which is within the microcontroller but not within what we call the processing unit or the CPU, right? That is remote to the processing unit, right? And we also discussed something called instructions, which basically instruct the computer or the CPU to perform a certain operation, right? And that operation, as I said, had two components. The first component is what operation to perform, whether it's an addition operation, whether it's a multiplication operation, and what are the operands, right? If it is going to read from a certain location, where is it going to read from? Is it a register or a memory? And after execution of the instruction, it might try to write the instruction somewhere. So it is a destination register or some destination memory location, right? This is what comprises of a typical instruction, right, in a microcontroller. And specifically, we looked at AVR instructions, which is mostly suitable for this kind of IoT applications, microcontrollers. So the instruction set is agnostic of particular. We are not, when we talk about instruction sets, right? This is nothing specific about AVR or any specific vendor, right? It is general. It could apply to Intel, which has this x86 instruction architecture, or Qualcomm might have their own, Texas Instruments. So all of them, right? They actually can adopt a certain architecture set, right? Intel could have their own, or ARM based processors, they have their own, AVR, they have their own, and so on, right? And what we are looking in this class is very specific to one set, because we can't cover a whole lot of things. So just to give you an idea about microcontroller programming, we are taking one examples, and this is pretty applicable for many of these applications in the IoT space, right? This is 8-bit CPU, and whatever we are going to learn will be much more less complex, right, compared to what you learn in x86, right, Intel architecture set and all. They have a lot of more functionalities, parallelism, they might have multiple cores and so on. So those are much more complex instructions. Okay. And we also explained a little bit about whether how many operands go with a particular opcode. So sometimes you might have as little as 0 operands, right? Things like sleep, right? When you send the CPU to a sleep cycle, right? It basically, throughout the clock execution, it doesn't do anything. There is even something called NOP, right? Many of you might be familiar. NOP means no operation, right? It is going to execute though, right? The program counter is still going to increase, but in that particular address, if you write something like NOP, the opcode for this is often like 000, like all zeros. They don't do anything, right? Still, it's just execute some. It doesn't execute anything, but the program counter sort of increases. There could be one operand, as I said, increment, decrement, right? So you do a variable, like we often in a C program, I do I++, right? So this is like an increment operator. For the variable I, we just increment the value by 1. So often this is directly converted to an assembly level instruction called INC, right? And I could be something that is already loaded in the register, right? Depending on your program. Or it could even have 2 operands. For example, the swap operation that I spoke about, like exchange. This is very specific to this particular instruction set in AVR. XCH, there could be some other name in another instruction set, but in this particular case, this is known as XCH. Like address is where I want to take the data from, and another is the register where is another place where we want to swap the data from. So ADDR is one address location. We take the value from ADDR, and RD is another location, and we basically interchange these two values. So this is another example where we use an opcode with two operands, right? One is the ADDR address, and the other one is the destination register's address. Okay, so the way these addresses are referred to, right? If you look at the manual, there are certain ways, right? Direct register addressing, indirect register addressing, and so on. So we will not go into that much details, but when I mention about memories, I'll touch upon that. But it is your sort of duty to go into just know, right? What are the addressing modes, right? How are things loaded, right? Often it could be that the register stores the address, and what you are loading is basically contents of that particular address. Instead of explicitly saying the address location, right, because this is like 16 bits wide, so you might say which register stores the address. So the computer will basically treat that particular register basically as a pointer, and then it will redirect it to the particular address, fetch the data. Right? There are many ways you can fetch the data, right? Either you can explicitly pass the value, or you can, as we call it, like pass by reference, right? In that case, the address is often stored inside the register. Okay, so this was about the instruction set, and I asked you to look at the basic instructions that are supported in an AVR in this kind of an architecture, right? So there are 120 plus instructions, and please try to look at them. You are not asking you to memorize them or even remember anything, right? What I need you to do is if you try to read an instruction, right, whether you understand what is written there, right, in terms of the program counter, it's very important to know to read a manual, right? Then when there is something new, right, it would be able to understand and appreciate what is going on, right? There will be some mention of the clock cycle, how many clock cycles is it taking, whether it is what is the any other flags that are actually impacted because this instruction is executed. So these sort of things will start registering in your mind. So when you try to look at newer instructions, when you are trying to look for a new instruction, you basically sort of know how to study them, right? How to look at them. Okay, so that was the reason behind me telling you please look at the instruction set. Okay, so initially it might look boring, but you have to have that motivation that if I down the line, right, if I want to program something in assembly code, right, for as you will see in many of the cases, we directly need to execute assembly level instructions for making it very fast, right? If we go through libraries, as I'm going to tell you then in the next class, things could be very slow, like as much as 20 times slower, right? We are going to say that how much the assembly code using the assembly code directly helps you, right, in this kind of low resource systems, right? The system is already very slow, and by executing a lot of instructions which going through a pipeline of these libraries, right, makes them unnecessarily slower. Okay, so that is the reason, right? You should start appreciating why as much as we have to go closer to the hardware. Okay, so that was the suggested reading, and today we are going to look at the peripherals, right, to some extent, and like how they are interacting with the memory and so on. So we sort of discussed that there are these timers. We will come into details about what they mean and how they keep count of time. These are again some kind of a counter, right? It basically with every clock pulse, it is going to count a certain number, and there is a maximum limit based on the size of the resistor, that how much it can count, right? So if you know what is the time taken to increment the counter by 1, that multiplied by the size of the counter will give you an idea of the time, right? So suppose you want to basically count 250 milliseconds, right? So you can pre-decide what should be the value of the counter in order to make sure that 250 milliseconds have passed. So once the 250 milliseconds have passed, you can very quickly do certain thing, right? So every 250 milliseconds, suppose you want to blink some LED, right? So those are the things where you can use this counter or these timers, right? The other peripherals we are going to talk about is like where we interface analog sensors the signal value is not discretized in terms of the amplitude. So we, in a digital computer, we need to feed digital signals. So for that, we need this analog to digital converter, which is one of the most important components inside a microcontroller, because one of the basic tasks of this microcontroller is to interface sensors, and many sensors out there are analog sensors, right? So this is up to the ADC to convert them into digital form, and we'll have a detailed class on ADCs, right, and how to use these ADCs in a microcontroller. And however, there are other sensors which are just going to give you digital data, right? Instead of giving you analog data, they will convert it into a digitized form and send the data out to be consumed by the microcontroller. However, you need to have certain rules for negotiating how to fetch the data, right? The sensor will not understand any arbitrary way to get the data. So there are certain ways you have to interface them, and I'm going to teach you two specific interfacing techniques that hardware also exists in these microcontrollers. One is the serial peripheral interconnect, SPI. Some of you, if you have interfaced these sensors, you might already know, but there are some theory behind it, and why should you choose SPI over I2C in a certain case, or choose I2C compared to SPI in a certain case. So there are these questions that exist, right? In case you have the opportunity to, if suppose you are giving this task to some vendor, right, to design your sensor, and you want to have a like digital sensor, and you want to tell them, right, what kind of a protocol that you want to use, you can take those kind of decisions depending on your application needs. For that, you need to know the pros and cons, which one consumes more power, and so on. So there are like some differences, right? And also in terms of circuitry, right, whether which will take much more hardware real estate, right? So there are these how many which will take more pins and so on. Okay, and then we'll also briefly spoke about the general purpose IO. So these are the input output lines for connecting the analog digital sensors. Okay, so and these ones all reflect somehow inside the memory that we are going to talk today. And there is other thing called interrupt, which basically forms the backbone of all processing, all sensing applications. Is whenever there is some execution of a job and the sensor data arrives, somehow you have to stop the execution, and then what we call it as like something like an interrupt, so that your job is interrupted, and you need to serve the data that has come from the sensor. You have to store it in a memory, or run some computation, and so on, right? So we will also touch upon that, right? So all these peripherals, right, we are going to touch upon, right? And then once we have a good idea about these peripherals and what is the theory that goes behind them, we are going to see how to interface sensors, right? That so we have to understand something about this ADC, something about what is this analog comparator, how could they be used, something about these digital buses, and so on. And then we basically will write code or try to give you some examples how simple sensors could be interfaced using these interfaces. So microcontroller is nothing but it will teach all these concepts, right? We have spoken about this AVR core, that is the core CPU part, right? We have spoken about so many registers, the controller logic, the clock. You also have these digital buses, analog buses, ADC, timers, GPIO, right? All these things will come in a package, right? So this is what is known as a microcontroller. And what is a microprocessor, by the way? Any difference with this? Anybody?
Microcontroller has peripherals along with the microprocessor.
So what is missing in a microprocessor?
Memory.
Processor will have only a core, and it won't have proper inputs and outputs and these data bus architectures to in it, and don't even have a memory part in it.
So what memory? The registers are not there.
I mean, kind of the secondary memories. Like microcontrollers do have an like few controllers even have an uh, embedded memory in it. Like they have an
So
EEPROM along with
memory
it.
means RAM.
Sir, microcontroller is it's a collection of all the things. It has the CPU, I/O, memory, all those things. While microprocessor is only the CPU part.
Just the CPU part. Very good. Right. So all the interfacing circuitry, right, that we have seen around the CPU, right, whatever the green part, right, as well as the clock. So uh, this is the core microprocessor, right? Particularly the green part, right? In most of the microprocessor, you need to also supply the clock signal. Whereas in a microcontroller, the clock will also be, there'll be an internal clock also, right? And all these peripherals are not there, the flash memory, everything, right? There's nothing there. So just the CPU, right? To concisely define that, it will be like CPU on a single chip is a microprocessor, and you need to provide all the interfacing circuitry, right? How do you like basically clock that microprocessor, and then how do you load the program and all those flash memory, everything, it will be outside. Okay. And no things like all these analog comparator, ADC, everything, right? So it will just provide you the computation. So you have to pass it an instruction, it will execute that instruction and give out the result, right? It does have the registers, right? Because those registers are internal to the CPU. So it will have those registers, but nothing else, right? And you have to read the result out. That's all. What the microcontroller gives you, that all the entire computer is on the chip, right? This flash memory, you can have a little bit of application program that is running, right? That should be in the microcontroller. And then all these peripherals, as somebody said, timers, and you can have a ready-made circuit that is already built to interface with a sensor, right? So that is the difference. Please keep that in mind, right? So once we talk about microcontroller, this is already one bit ahead of a CPU, right? It already has a CPU inside, plus there is a lot of other things, right? That's why I said the CPU plus plus, right? CPU is just the microprocessor part. And as you know, there are a lot of vendors. This microchip was the new vendor which bought Atmel, right? And then there are other very famous microcontroller vendors like ST Microelectronics. So they will do all this ARM 32-bit microcontrollers, and then this NXP is nothing but this Philips semiconductor, right? That got rebranded as NXP. So these are very big players, right? Intel might not be a very big player in the microcontroller part, right? Most of the popular IoT devices will use ST Microelectronics, Microchip, NXP, Broadcom, this kind of microcontrollers. And many of them will follow very similar architecture sets, right? ARM instruction set is one of this. Many of them just follow the ARM instruction or ARM architecture. And in this case, what we are doing is with Atmel is the AVR architecture. So the philosophies, as I told you, they don't change much, right? Of course, there is a difference in between x86 based instruction as compared to what we are doing. There is this RISC versus CISC thing. But when we are in the RISC domain, right, simple instructions and much more efficient instructions in terms of clock cycles, it will all execute in a single clock cycle, most of the instructions, right? They are very pretty similar. Okay, so you can take a look at the different instruction sets that are available, or what are the vendors which are producing them, right? What is ARM and what is AVR and so on. Okay, so with this we'll we'll very specifically introduce this Atmel 8-bit AVR microcontroller that actually costs something like 150 rupees if you want to buy the IC, right, the microcontroller IC. And this fancy form, right, which is we call this Arduino Uno, for example, that costs like 500 rupees in the market, right? If you buy it online, it costs something like in the order of 500 rupees, which is 3 times the cost of this microcontroller, right? And I also tried something which is in between, and you will also find a lot of DIY videos in YouTube, right? All you need is to have a very simple interfacing circuitry, put an oscillator. So what I have here is the crystal oscillator for producing a 16 megahertz clock pulse, right? Even if you don't have it, there is an internal 8 megahertz clock inside the microcontroller, right? So If you don't want any more speed, right, that would be good enough. And you can put 16 megahertz for doing it a little bit faster, right, 2 times the clock speed. And this will also give you an experience, right, give you more confidence, right? Just buying a directly a microcontroller from the market, you can program them, right, putting some very simple interfacing circuitry. And this is pretty simple. There is a lot of blogs and like videos, right, you can watch, right, people doing that. It's not just about the cost, but also for your experience. Okay, so if you have access to this kind of things, right, if you are into it, then you can, like, it's worth getting a try, right? Okay, so from whatever I have taught you is on the right hand side, what was the generic piece of microcontrollers, or particularly the CPU, the green part, right? And if you see on the left hand side, that is directly from your data sheet, right, or the data manual, right? That was the other document that I also shared and asked you to read about the CPU core, right? So if you see, all these things are sort of known to you by now, right? This ALU is the arithmetical and logical unit, which is directly interfaced with the general purpose registers. We call them general purpose registers. So there are 32 general purpose registers. Each is 8 bits, right? A 1 byte register. Okay, and these are the things that I was asking you to look at. So the way the data is fetched, there is something called direct addressing and there is something called indirect addressing. So this is basically whether you are trying to fetch the data directly from your memory or you are going via registers. Okay, so if you are going via registers, right, the registers sometimes store your address, and in that way you indirectly fetch them. So I would request you to look at them. It is for your knowledge, right? Sometimes there are, like, for making things scalable, right? Sometimes you often don't know the address beforehand, right? In those cases, you cannot really hard code that address in your program, right? So it has to be dynamically generated, or you need to compute the address somehow. So there are these different reasons for using them. Okay, so it's better if you look at it, right? And then you already know about this instruction decoder, which goes to the control lines, and you are aware of the program counter also, which basically keeps track of which instruction is being executed. The control is in charge of that, and flash memory is something that we are going to cover now. So it's basically going to have the application code. The code is resident there, and the code is basically going to be fetched based on the program counter's input, and it will be executed, right? So basically the instruction register is there, which contains the current instruction that will be executed from the flash memory. It has been fetched, then the instruction will be decoded and executed. So most of these things will start looking familiar to you, right? And then there is a data static RAM. When the program is being executed, all the bookkeeping variables will be kept there. All the variables that you declare dynamically, there are things that are declared, and there are sometimes some of the memories are freed and so on. Everything will happen inside that SRAM. Okay, so there are IO lines, and there is EEPROM also. There is another part of memory which is also non-volatile. It's not very commonly used in most of the cases, but there is an option also to put, there is some extra memory inside the microcontroller also that is often used if you need something more beyond the flash as well as the SRAM. Okay, and these are the peripherals on the right hand side. There is an interrupt unit, the SPI bus, analog comparator, IO lines, and so on. So this is about the different things that you have inside the core or inside the microcontroller. So you have to basically look at the specification, right? Once you look at the manual, so this is mostly about the memory, flash, SRAM, and EEPROM. So depending on your application, this is very, very important, right? What kind of application you are targeting, right? Based on that, you have to buy that kind of a that packaging, right? The instruction set doesn't change, but your packaging might change. What might happen is the flash could be reduced or increased, or the number of GPIO lines, right? This is general purpose IO lines. We often call it GPIO. So you might not need 23 GPIO lines, right? Or you might not need this 2 kilobytes of SRAM, or you might need very little. You might have a very simple application, right? That is maybe a few hundred bytes of code, and for that you don't want to waste this much memory, right? So most of these microcontrollers will come in various forms, various memory sizes, various number of IO lines, and your cost will also decrease based on that. And not only the cost, but also in terms of power, that will be less power hungry compared to if you go for higher and higher, right? So you have to look at a series of microcontrollers once you visit their website, right? If you go to Microchip or Atmel's website, if you mention what kind of memory requirements you have, you will basically get a suggestion of multiple types of microcontrollers that might suit your purpose, and then you have to choose based on your exact requirements on dollar cost or power, right? And these are the peripheral interconnections, right? If you want to connect certain sensors, right? So these happen to have 2 SPI buses and 1 I2C, and this is for serial data transfer, ADC. So suppose you want 12-bit ADC instead of a 10-bit one, right? Then you have to look at some other microcontrollers, maybe at higher ends, right? So if you really care about the resolution of your data that is coming inside your from analog to digital conversion, right? That we are going to study later. Many of you have a preliminary idea, but right, this 10-bit might be not sufficient for you. You might need 12 bits, right? You might need 14 bits, right? So it's very intensive to some kind of analog sensor, and you want to be very precise. So these are the different things you have to look at. So if you look at the manual, they give you this configuration summary, right? Same with timers and counters. You might need more of them, right? So there are various ways to make the maximum out of whatever has been there, right? So with this 2 8-bit timers and 1 16-bit timers, there's a lot of things that is possible, just that you have to use them intelligently, right? So whatever has been given you is sufficient for most of the cases, but yeah, in case you want something which really doesn't suit your purpose, you have to look for something else. Okay. So we'll start with this. We'll go one more time over this Atmega328 architecture, but most of these things you will know because we have already discussed, right, the different components. It's just to make sure that you are starting to feel familiar with whatever is there in the data sheet. Okay, so you need to basically start looking at these things and appreciate, right? Whatever you have learned is you can understand by looking at the data sheet. So this is your AVR CPU, or whatever we call the microprocessor here. We mention it like MUP, and we are already aware of the flash memory and the static RAM, that is for the data, right? Your runtime data and your application is here, right? And then there are other things like oscillators, which is going to drive this entire engine, right? All the clocks and everything. EEPROM is something that we spoke about. There is power management, and this is for debugging, the debugware. And anybody is aware of what is this watchdog timer? Because there are some nice examples behind it, like in all these microcontrollers, right? Watchdog timers matter a lot. And anybody know what is a watchdog timer? It's very useful.
It's kind of a timer that goes on, and when the microcontroller is on, and when generally there is some kind of an
Your voice
unexpected
is
operation.
breaking. Sorry, sir. Your voice was breaking.
Sorry, like it's moreover like kind of there's a nice analogy for this, like it's kind of a person with a stick and a dog there. So it's like this timer goes on running, and when there is an intrusion in the operation, or like there is something that's going unexpected, then when the it's just resetter. When there is something that's unwanted happen and there is no flow to this resetting function, then this timer goes on and it generally restarts the whole system to make it not
Right.
go out of bound.
Yeah, yeah, you are right. So it's something unexpected happens that, like, very often, right, we'll run in an infinite loop, right? In a regular computer program, you have all written in your first year of BTech, right? You write a program and that program runs into an infinite loop, and you have to basically press something like a Control C, right, to basically kill the program, right? But in a microcontroller, right, there is no operating system which is governing the entire flow of instructions, right? If it is stuck in an infinite loop, or you do something illegal, right, which in your code, that somehow hangs the system, right? So in that case, your program is going to check this watchdog, right? It's like a dog that is like watching your system all the time. And if you are doing something for very, very long, it is going to reset your system, right? It will somehow understand that you are taking too long. Your program might be crashing, or something is wrong with the code. So what it will do is it will basically reset the timer. Right, then all your operation, what I've been doing, is all gone, right? It will start fresh, right? Just to give you an anecdotal example, right? This is something I picked up from the news, right, when I was reading about it. So all of you are aware of this Mars helicopter, right? Somebody from our IT Madras was also involved with this flight, right? This Perseverance, a Mars helicopter, right? So do you know what happened here with respect to this watchdog timer? First of all, do you know it was like the scheduled flight was delayed, right? So if you go to NASA's website, you can actually read up what really happened, right? I'll just going to read that for you. So if you see, right, based on the data from this Ingenuity Mars helicopter, right, that arrived late Friday night, NASA has chosen to reschedule this Ingenuity Mars helicopter experimental flight no earlier. So what was happening is, during a high-speed spin test of the rotors on Friday, the command sequence controlling the test ended early due to a watchdog timer expiration. So what the watchdog timer thought is, it's taking too long. So there was a series of instructions that was getting executed, and somehow the watchdog timer thought that it's taking way too long, right? It should not have taken that long, and it just basically reset the entire system. So it occurred that it was trying to transition the flight controller from pre-flight to flight mode, and that basically jeopardized the entire process, right? It had to start afresh. Right, so if you see the watchdog timer, what does it do? Oversees the command sequence and alerts the system of any potential issues. Right, so whenever you write a program in production, right, and you don't want to, somebody buys your system, right, and they don't have any sort of interfacing. If you sell that IoT product, it basically hangs, right? Somebody has to go and restart the system, and often people might not do that, right? Suppose it is a system which is perpetually on, okay, like a surveillance camera or something of that sort, right, where people doesn't go and attend the system every now and then, right? So you have to have a mechanism to know that something in the code is going wrong, and one of the ways to do that is to have an interrupt using this watchdog timer, right? So this is something which is really useful in a microcontroller based application. Okay, so if you are not aware of this watchdog timer, please go and read about it. It's called watchdog timer, right? And then there are associated interrupts and so on, right? So I will of course teach you about interrupts, but this watchdog timer is a very special kind of thing that exists in microcontrollers, right? And there are more even things like accidents, right, that happened in all these earlier days spacecrafts, right? So if the watchdog timer was not firing properly, you could burn a lot of fuel, and all these things happened, right? There's a lot of stories you can check out, right, regarding the malfunctioning of what these watchdog timers.
Sir?
Yeah.
Sir, yeah. What exactly does something going wrong mean? You said that the watchdog timer will send an interrupt.
So see, every time, right, the way it is implemented, once you execute a certain code fragment, you are supposed to go and do something with the watchdog timer. Okay, so what we call like feeding the dog. So we give an analogy that the dog is watching your system running. So you execute certain thing, and after that you are just going to go and give a something like that you are present, right? You are executing that thing, right? Go and report that to the watchdog timer, so it knows that whatever you are doing is expected. But suppose you are not reporting to the watchdog timer for a pretty long time, which means that your code has been lost somewhere, right? Suppose you are going into a system crash, or the program heap memory is getting expired, right? It's basically it's so large, it's getting crashed, right? Or there is some memory corruption, right? For these reasons, what happens is your code has taken an unexpected turn. For that reason, you are not going back to the watchdog timer reporting that yes, I am alive, my code is alive. Okay, so nobody is reporting it, and the way it is built is that once your program is not reporting back to the watchdog timer, it will think that something is wrong, so I will reset the entire system.
Okay.
So wrong could be many things, starting from memory corruption to infinite loop. Many things could be there. Is it clear?
Yes, sir.
Okay. So please ask questions. So whenever you have doubt, and also it will help others, right, to understand, right? Please ask questions. Okay, so that was the other part of the lower part of the CPU zoomed up. So this is more about the peripherals, right? So now you are basically starting to get familiar with these different things. Right? Earlier, whatever was there was particularly with the CPU and the interfacing of the CPU with the memory. Now these are the peripherals like SPI. This is the I2C or the two-wire interface. Some people call it TWI, two-wire interface, and I2C is basically a thing that was coined by a very specific company. We'll talk about them later. So they use this term called TWI, and these are the ports which are nothing but this input-output lines, and some collection of input-output lines are called ports. So we'll know why are they called ports and how to handle them. Mind it that this is specific to this Atmega microcontrollers. Okay, these are the timers. These are 16-bit timer. We have two 8-bit timers, and all these timers are something that we can use in our code. Suppose you want to run two timers, right? So one idea is to use this TC0 and this TC2. Okay, and suppose you want to count for a long time. So in that case, instead of using this 8-bit counter, we are going to use a 16-bit counter, right? So it can go to 2 to the power 16 minus 1. So your delay that you can actually produce there will be pretty long. Okay. So, and then this analog to digital converter is always there with some of these inputs that A to D converters take. There's a reference voltage, ground, and so on. And this is pretty much it, right? So all these things will help you for sensor interfacing. Okay, and this is the A to D part if it is an analog sensor. If it is a digital sensor, so I would say this is for digital sensor interfacing, because all these are digital buses, right? SPI and TWI. And this is for serial communication. If you are trying to send out some data to another device, transmission and reception you can do using this UART. And this is for your internal logic, right? If you want to wait for a certain time, then read a data or send out a data somewhere, this timers will be very useful. And it can also help you to generate signals, right? Suppose you want to do some kind of a sensing where you want to transmit a certain signal. Let's say you have interfaced a certain speaker, right, where you want to send out a sound signal, an acoustic signal, right, and then try to get the reflections coming back, right? Based on that, suppose you want to implement some sensing solution, right? So these timers would be used to generate signals, okay, which is very useful often, right? If you want to like not just have a passive sensors, but you want to do something actively, you want to send out signals, and based on how the signal interacts with the environment, you want to draw conclusions. So in that case, you want to do something like that, right? So this is something that is digitally generated, not something that like our infrared thing was that you just connect high voltage, it is going to emit an infrared light, right? Infrared signal. Not like that. You want to curate some kind of a special signal. In that case, it will be necessary. Okay, so now I'll come to the memory architecture. So first is kind of a logical view, right? What are the different components in the memory? As I said, the flash memory is one of the first things that should come into our minds. So it has these two parts, right? One is the interfacing software as well as the data handler. That is what we call is the application program, right? And there is something which is very special called a bootloader, right? We are going to talk about that. That is also a piece of code that resides in the flash memory, which is separate than your application program. So in your flash memory, there are two things that will be existing. One is your bootloader code that is already there, that's not written by you. That is, of course, you can have your own bootloader, but that is nothing to do with your resident program, right? That is doesn't depend on the functionality of your program, right? And then apart from the bootloader, you will have it. This is your program, right? And there is only one application program that you can write, and there is one monolithic sort of code that goes there, right? And it will, as you saw earlier, your computer will keep on executing that particular piece of code. Okay, then we have already known about this set of registers, often called register file. I'm basically presenting you a logical view, right? So it's all part of certain, it's all part of the same microcontroller. I'm trying to give you the different flavors, right? The different meanings of different portions of the memory. So the register file is nothing but access to the CPU registers. There are 32 registers in this case. So it could be identified by a 5-bit address. As while we were discussing the instruction sets, we are seeing that many a time we are just trying to address a register using 5 bits, right? So some of these could be chosen, right? These are general purpose. If you want to use it for your own computation, you can do that. Then you have this SRAM or the static RAM, where this is volatile. Once you switch off the computer, once you switch off the microcontroller, this contents will go away, whereas the contents in the flash memory is not going to go away. So this is for program bookkeeping, right? You initialize variables, you declare an array, you generate an array there dynamically, you free some memory, it is going to be freed there. So all your program specific data will be residing on the static RAM. Okay, the program stack, the way we call it, right? And then once you have the sensors and the interfacing hardware, there are dedicated memory for handling these IO lines, right? So these input output lines are all mapped to certain portions of the memory, right? Any particular pin, right, that you are attaching to an interfacing hardware or a sensor, that is always mapped to a certain portion in the in your memory. So you have to know, if you are reading from that particular memory location, you are actually reading from that that sense, you are basically reading some sensor data, right? That's how it's all organized. Okay, so these input output lines are also represented in, there is a direct mapping in between the input output lines to portions in the memory, and we will see how and what are the functionalities and so on. Some of these could be actually used to configure even the interfacing hardware. So let's say if this is an analog sensor, interfacing hardware could be an analog to digital converter on an ADC, right? So suppose it's an analog sensor. Okay, and now there are certain things that it has to be configured inside the ADC. Okay, so those configurations, we will later know what are those configurations and so on in this particular context in later classes, but this could be actually configured. There are predefined portions in the memory that will be responsible for configuring various aspects, right? There is not just a single aspect, right? There are various aspects inside an ADC, right? And every bit here, so there are 8 bits in a given location, right? So every bit has a special meaning, right? And they have done all this tedious task of gluing it up all together in the microcontroller, right? This is a very, very tedious task. As you will, if you see the manual, if you start appreciating these things, right, you will see how complex this simple microprocessor could be, microcontroller could be, right? And then there is this EEPROM, which is non-volatile storage also, but it's not always used in the frequency we use this flash memory or this input-output files, register files, SRAM. So suppose you want to have something statically stored, right? Let's say there is some company logo, right? You want to actually load from time to time. Show it like in your Android applications, you have these splash screens often, right? We used to have them. When you start an Android program, they will show something and then go to the main program, right? So often those kind of things, some pictures it could store, right? So you want to expand the application program as much as possible in the flash, because that is where your application program resides. So you don't want to keep any unnecessary things that is not required in their flash there, right? You want to have as much logic, programming logic packed in inside the flash, and whatever could be some constant, some other things that is not needed from time to time, you could put them in the EEPROM, right? And as you see, this continuous thing is all balanced, like all controlled in this microprocessor. So the processor sort of reads this application, right, and that all this execution thing, whatever we have discussed earlier, execution, right? So reading all these things line by line, so byte by byte, doing all these instructions, decoding, and all these things happens here in the processor, right? So this is how memory plays a very, very critical role, right? Whatever I have drawn here is the processor, and there is this bunch of peripherals on the left hand side in gray color, right? And this memory, right, it sort of play a very, very important role. There's so many flavors, right, inside just the memory, because people who are not introduced to this kind of systems, we generally think that there is just only one memory, nothing else, right? But memory has these slight variations, right? And there are different purposes of using different portions of memory. There are best practices, and there are certain things that you have to do or have to follow. Okay. And even there are sophisticated things that I might not mention right now. Is suppose you are packaging this. I'm not going to go into like much details, but I'm just trying to mention. Let's suppose you are trying to do a production hardware and you want to lock the code that you are writing. Even those kind of things are possible, right? Suppose you want to lock your application program so that from outside, right, nobody is able to retrieve the code or change the code. Let's say, right, somebody might actually erase everything, but they cannot, let's say, change or manipulate the code. Okay, so or they cannot change like any touch the bootloader, for example, right? So these are just adding some security bits to your IoT hardware. Okay, so this is nothing central to any microcontroller programming, but it's good to know about these things, that these things are possible. Okay, like the way we do all this code obfuscation in your APK file, right? Suppose you want to generate an Android binary, and once you give it out to the world, right, people can retrieve the binary and basically try to decompile the code, right? Suppose you get the APK file for Facebook, right? It is very difficult to actually backtrack, right, and generate the actual code that created the Facebook's binary APK. Okay, so they will do all sorts of code obfuscation, and if you, in these case also, right, if there is a proprietary code that you don't want the world to know about, so there are ways to lock them. Okay, so about details of the memory architecture. So the application flash section is there from 0000 to a certain portion, and the rest is taken by the bootloader code, right? So in all, we are putting it as FFF, and then there is a 3. So can somebody tell me what is the size of the program counter in order to parse through this set of addresses? So it ends at 3FFF. What is the size of the program counter? What does the program counter do? It's a very simple question. Like somebody who knows, just give me the answer. But it needs to count from, yeah. Hello?
Is it 14 bits?
Yeah, very good, thank you. So you have this 4 into 3, 12 bits, right? And then there is this 1, which is 2, right? So this is 12 plus 2, 14 bits. So you have a 14-bit program counter, which is sufficient to go through this address space. Okay, so this is all about your program memory or the flash part, right? Okay, and then apart from this, we also have this registers, right? We mentioned this general purpose registers, this 32 registers, right? That is within the CPU. And then there is this input output registers. As I mentioned, you can interface various sorts of peripherals and configuration of those peripherals here. So it could mean different things, and those details are given in the instruction manual, and I'm going to show you some examples. And then there is this free space that you can use for your programs, right? So this is specific to the microcontroller that we are studying here, right? This Arduino's microcontroller, this Atmega328P. Okay, and even if you follow the address, right, so it starts from 000 to 1F, which is nothing but 16 plus 15 is 31, right? So 0 to 31, so there are the 32 registers. So starting from there, you have more of them. So this 32 and then 64, there is 96 plus 160, this will make it 256. So there are 256 registers, right? This 256 bytes that you keep, and after that you start your SRAM space, where you basically have the program stack and the program heap, right? You have the runtime stack and all these heap related things, and your free space where you store all the variables and everything, right? That we just now told you about. Okay. So this is about to give you some details. You can't read them; they're very small. But I just give you some examples of these I/O registers, right? So on the left-hand side, you could see the address. So if you follow here, so this is the address. The offset is offset from 0, let's say, right? So 0x23 is 16 into 2 is 32 plus 3, 35. So is the 35th byte, which basically has this functionality, right? There is a name for this, and there are certain ways, like there are certain meanings to it. For that, you have to go to the instruction manual and understand what they mean, right? So I have done your job simpler, just to gauge the usefulness of this register files. So one could be used for this, a set of them could be used for this digital I/O ports, right? If you look at the Arduino, you will see that there are these digital pins, right, from 0 to 13, right? And all of them, as I told you, there are certain ports, and you can configure them as inputs, you can configure them as outputs, and so on. But everything is controlled by this memory. Okay, although there are APIs to do them, but these APIs are nothing but they will go stage by stage and do something with this memory, right? And more APIs you use, you will basically waste a lot of the program space, right? Your program unnecessarily becomes very large, right? To do a very simple job, you have to go through 3 or 4 function calls, right? I am going to demonstrate that in the next class, how much big it unnecessarily becomes and how much slow also it unnecessarily becomes, right? So as you see here, a section of your register IOs are linked to what you can do with this digital IO pins. Another example is with the ADC, right? If you go and see towards this section, right, 0x78 to 0x7c, there are certain registers that are useful for configuring the analog to digital converter, right? And in an Arduino, if you see, there is this A0 through A5, there are the 6 ADC or analog pins where you can give an analog input, right? And that analog input internally has to be converted to a digital form before your program interprets them, right? My digital computer cannot interpret analog values. It has to be a digital value in order to understandable by the computer. Okay, so in this way, these are all, as you can understand, there are certain peripherals, right, which could be configured using this set of already declared registers, right? Already declared, and then there are some reserved ones, right? These are something that you can take control of, but not the ones that has already been registered as a part of the specification. So these are already hard coded, right? In your hardware. So in the hardware itself, these registers are specifically kind of hardwired to certain peripherals. So you cannot change all these things, right? So this is how you want to understand this part of the memory. Okay, so next time you look at them, right? Suppose you want to deal with a certain particular thing, let's say a timer, right? You have to see what registers are responsible for controlling the timer. Right? In that way, you have to know each and individual. So these are bits, right? This is bit number 0, 1, 2, 3, 4, 5, 6, 7. Okay, so maybe this is not the one. So starting from this is 0 and this is 7. Okay, so yeah, this is some version number or something. So each and individual bits will mean something. Okay. So about the bootloader, I'm going to give you an introduction to what is this. So what it does is read this thing very carefully. Read while write self-programming, it is called. So it is going to read from somewhere. The bootloader is a piece of code. At the same time, it is going to write that to the flash memory, right? So it is residing in the flash memory itself. One part of the flash memory is the bootloader, and what it is going to do, it is going to read. So there is an appropriate data interface where we are going to pass on the application binary. It could be your computer or some other microcontroller even, that is also possible, which is going to transfer the code. So this, whatever I have written is the binary code that is going to be written to your application memory section. So the processor is going to take that through some data interface. And how it is taking that? Because it is the program that is written in the bootloader. The code is executing, the code in the bootloader is executing, which basically does all the job. It's somehow reading this page after page from your other computer and then writing them to your program memory. So that's all the bootloader will do. And then it is going to point the program counter from where the program is supposed to start. So these are the two things they will do. Okay, but still it is pretty inherently complex because they have to start different mechanisms, right, inside the microcontroller, right? So this is the bare hardware that somebody has given you, and the bootloader sort of brings life to it, right? All the different hardware has to be initialized with proper values, right? The different memory locations they have to point to, right, to make it functioning, right? You have this BIOS in your desktop, right? The way it basically chooses an operating system and loads that operating system in memory. Here we don't have any separate operating system. What we only have is the application code, and what the bootloader will basically do, it is serving as an operating system, as if, right, get the code, right? This code is somehow equivalent to your Windows or Linux, right? That is going to be loaded now, and then it starts executing. Okay, and this is your application code. Okay, this is your application code. And if you are curious, you can look at some of the recent bootloaders that are being developed for these Arduino kind of devices. So there is something which is this is really smart. I think if you are interested, you should actually look at them. This OptiBoot Bootloader, it's actually packed within 512 bytes of code. So 512 bytes does all the job I told you. So if you look at the manual, so they will say the program code within the bootloader section has the capability to write the entire flash, including the bootloader memory. So this is such an intelligent program, right? This is going to eat itself up, right? And it's going to expand the space for writing application memory. That's why we are saying that read while write. So it's reading and writing, and it might happen that once the entire thing has been written, the bootloader is non-existent. The bootloader is gone. Okay, so that much of intelligence could be packed inside the bootloader, right? Often you don't need this bootloader. Whenever your program starts, it could start from 0000, right? That could be the default value, and then you keep on executing your program, right? And nobody is going to load any program later, right? This is an production hardware, right? You don't need to change anything there. Okay, so a bootloader can thus even modify itself, and it can also erase itself from the code if the feature is not needed anymore. So you might not need a bootloader, and this is from the manual, like Atmel manual. You can check that out. So this is there is a certain section called the bootloader. If you read that up, right, like there are a few pages, 5-6 pages, you will get a much better idea, right? And this is the machine code, right? This is the machine code for the OptiBoot. This is all the 512 bytes needed for doing this entire job. Okay, and if you are like really interested, this is open source, and you need a pretty good command in C program, right? C programming, and some knowledge about the microcontroller, and you can look at this code, right? This OptiBoot.c. There are many macros because they will try to make it more general purpose for a wide variety of microcontrollers, including the smaller versions of this Atmega or somewhat larger versions, right? But if you scan through it, right, you will get a general idea about what this tries to do. Okay, it doesn't try to do much than what I told you in 2 slides back, right? But to do it correctly, right, and to make it supported across this large number of hardwares, right, that requires a little bit more meticulous coding. Okay, but if you like this kind of things, you will enjoy, right, how this bootloader is done. And I already told you about the EEPROM. So this is basically acting as a tiny hard drive. If you need to, let's say you want to display some logo when your system starts, right? Or if there is a menu, right, that you want to dynamically load, you don't want to waste the application program space in doing all those menu items and some graphics and all. So those kind of things you can actually put there, right? In case you have an LCD screen and you want to display something in the screen, right? In those cases, this would be very handy. Okay. And often, right, instead of even using the SRAM, right, you can optionally write things to the flash also. We will tell you how to do that. So normally, whatever you do is as a part of the program will be all declared and stored in the SRAM, right? Right. You can optionally write it to the EEPROM using this EEPROM.h header file that gives you access to different functionalities. You can write bytes, right? You have to write a character and read a character from the EEPROM, or you can also, there are ways to write into the application section of the flash memory. That is also possible. Okay, so this is about the system development. If you want to get started, I would recommend, right, some of you already might have access, and this is optional. Again, I cannot force you to buy these things, but it is also going to make the most out of the class, right? This cost like $4.99. Actually, this line is missing, right? I use this website called this robu.in, but there are many other websites that you can use. Sometimes this is a very electronic specific website, so that's why I get a lot of other items here. That's why I buy them from here. But this could be even available in Amazon in very similar price range. And there is a cable that you will need for connecting the Arduino device to your laptop or your desktop computer, and that's all needed to program that, right? In case you want to buy some sensors, you can buy some cheap IR sensors or some other things, right? If you want to ask something specific, you can write me an email. We can discuss about if you're planning to buy something more that will also come handy for your project. And this Atmel Studio 7 is something that we really use for doing very deep embedded systems development. But in our case, the Arduino IDE would be sufficient, right? This is the Arduino IDE, right? This is kind of lightweight, and most of your job will get done, but you cannot do any sophisticated debugging. But anyway, we are not much interested in any deep microcontroller based debugging as a part of this course, right? We'll be mostly interfacing sensors, and as long they are interfaced properly and efficiently, we are happy with that, right? And we'll turn our attention in the way the sensing algorithm works or the different modalities of sensing, right? So if you are really interested in embedded systems, right, embedded systems development, this is something you can get, right? This Atmel Studio, this Atmel is bought by, I think, this Microchip, so it might have become this Microchip Studio, but you can do a Google search, right, and get this IDE, right? I won't recommend this if you are a beginner, so you can just simply get the Arduino IDE, and it makes your life much more simpler. Okay, and this is how you are going to install an application binary. Please install. My suggestion is, before the next class, if you have this Arduino available, please try to set up your system. Please have an IDE so that you can write some very simple code and upload the code to your upload the application to your Arduino and then see it running, right? So that's how you can access these different registers that we spoke about. You can write to the EEPROM, you can read from different registers and so on, right? It's just a fun thing, right? And it will also give you some hands-on experience and confidence. Okay, so these are the different peripherals we are going to cover. Next class, we are going to look at each and individual of these peripherals, and we'll get started with programming, right? Once we get started with programming, through that we will explore these different things, right? Counters and timers, and particularly these are the things, right? This two-way interfaces. So Philips is the name of the company, right? I was telling you that some vendor actually coined this term I2C. So the sensor interfacing. So these things we will do, this temperature measurement, all these things we will do as we explore, right? As we drive down through this course, right? One last thing that I want to mention is how these peripherals are clocked, right? So often you might think that like whatever clock that we are producing in this oscillator, right, wherever we are giving to the processor, all the components actually work at that particular rate, right? Suppose this is 16 megahertz clock that we have provided to the CPU, but it doesn't mean that all the components are actually operating at 16 megahertz, right? None of the peripherals are that fast, right? So it cannot keep up with the particular CPU speed. Let's say there is an ADC, let's say peripheral 1 is an ADC. So the way the ADC will function is it cannot actually support the 16 megahertz clock speed, right? It cannot turn out samples that fast. So what we need to do is we have to do something called a prescaler division. So there is a clock control unit which will basically take the frequency or the rate of the CPU, that is the F thing, and divide it by some kind of a prescaler, right? This prescaler could be some predetermined value that is available in the specification of that particular peripheral, right? If it is an ADC, the prescaler could be, let's say, 64 or 128 and so on, right? So you have to divide the 16 megahertz divided by that prescaler, and that will give you the effective clock rate of this particular peripheral. So peripherals are much slower devices than CPU, hence the CPU clock cannot be directly fed to the peripherals. Prescaler value is used to downsample the CPU clock to a reduced rate, right? So if this is 16 megahertz, this could be 125, let's say, kilohertz. Okay, this peripheral device could be 512 kilohertz, right? So these devices will be much more slower, and this is the master one, right? The external crystal oscillator is the maximum that you are giving to the CPU, that is the system clock. So this basically limits the maximum data transfer rate for a sensor, right? If it is a ADC, an analog sensor is connected to the ADC, so how many times you can get the data out of the ADC per second is determined by one, what is your external clock input, and what is the prescaler divide. It often the maximum clock that you can feed here, right, that is often mentioned in your data sheet. Okay, so you cannot do really more than that. That's the reason you will have to use some kind of an appropriate prescaler. So this is the logic. This is image that is already available in the data sheet. Please look into the data sheet. That is somehow representing the same thing, and you might have multiple crystal oscillators, right? So there is a clock multiplexer which is going to take multiple clock inputs, and at the end of the day you are going to feed only one clock to your system, right? So the system clock goes to this AVR clock control unit, which gives rise to so many things, right? There is an asynchronous clock, there is a input output clock, there is an ADC clock, there is a clock for the CPU, there is a clock for accessing the memory, right? The way you are accessing the memory, fetching the operands, right, fetching the instruction, it takes time. So there are some clock cycles that will be expanded there. So all of these different things will use some reduced version of the clock rate, which is much lesser than the main system clock. Okay, so this is a small takeaway, right? Because often we might think that if you are giving a 16 megahertz clock, everything operates at 16 megahertz, right? That is not true. there is this very important concept called prescaler, right? That determines, what is your maximum data rate for that particular peripheral, and in that way you are going to request the data. If you are requesting more data, the device is not going to answer. Okay, so with this I'll wrap up. So next class we will start more hands-on programming and give you some more idea. So now in these two classes you have fairly a good amount of idea about the microcontroller based systems. You have some idea about the memory. Now we'll try to see something in action, right? What are the best practices in coding, and how can you shrink the code, right? Once we do that, we'll start more on the sensing part.